Hello, and thank you for joining us. Today's webinar topic is Fundamentals of Purge and Trap, presented by Amy Nutter, our VOC Technical Product Specialist for Teledyne Techmar. We will be accepting questions, so please feel free to submit your questions throughout the presentation, and Amy will respond to you by email after the webinar. This webinar is being recorded and will be available within a few days. Now I'm going to turn it over to our presenter, Amy Nutter.
Hi, thanks for the introduction. I'm Amy Nutter, Technical Product Specialist for the Purge and Trap product line here at Teledyne Techmar. And today I will be going over the fundamentals of Purge and Trap. So this will be a great intro to this technique or a great refresher. So thanks for joining me today. I will go over a quick introduction to Teledyne Techmar and our products. Then I will get into what Purge and Trap is and how it works. And then I'll be getting into how the trap itself works and what parameters help create an efficient purge. Be sure to submit any questions that you have, and I'll get back to you via email. Teledyne Techmar has been around since the 60s, creating the first commercial purge and trap concentrator in 1975. We're the market leader for purge and traps in the US, and we offer several different options. The Lumen Purge and Trap concentrator, shown on the right, is our standalone waters-only concentrator that can be paired with the Aquatech LVA auto sampler. We also have the combined auto sampler and Purge and Trap concentrator, the Atomics XYZ, shown on the left, which is capable of analyzing soils, solids, and water samples. We also manufacture other elemental analyzers as well. The Purge and Trap is a technique used to improve the sensitivity of volatile samples analyzed by a GC and their detectors, such as a mass spec, and they go beyond the capabilities of other traditional preparation methods like static headspace and liquid injections. So we're talking parts per billion, ppb levels, and recently we've even been optimizing parameters for parts per trillion or PPT analysis. Some common VOCs are disinfection byproducts from chlorine treatment. Gasoline is made of a lot of volatile compounds. Ethanol found in beer, acetone in nail polish remover, mineral spirits and paint thinners, and hexane found in glues. Now let's get into how this works. So Purge and Trap works on a purge equilibrium theory or a disequilibrium theory, meaning that volatile compounds of interest, compounds that prefer to be in that gaseous phase, they migrate from the liquid or solid phase to the gaseous phase, and they are continuously swept away from the headspace in the sparger onto the trap where they're concentrated and then released to the GC. In the case of static headspace shown on the left, samples come to an equilibrium. The compounds of interest go from the liquid to the gaseous phase, and when no more net transfer is occurring, an aliquot of that headspace is taken and analyzed. If not enough sensitivity is reached during this static headspace analysis, then that's where Purge and Trap can improve. On the right, we can visually see that that purge equilibrium theory. The VOCs are moving into the gaseous phase and are constantly being removed by the purge gas. Continuously replacing that headspace causes that disequilibrium I was talking about, in that there's always a higher concentration of VOCs in the liquid phase than in the gaseous phase, creating the net movement of VOCs from liquid to gas, extracting the VOCs from the sample more efficiently and improving sensitivity, because there are more of those compounds to analyze. A basic Purge and Trap consists of 5 main parts: sparger, flow control, 6-port valve, analytical trap, and the heated transfer line. The sparger is the glassware on the front of the instrument that receives the liquid sample to be purged. Purging the sample extracts the VOCs by dispersing inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or a pressure regulator that monitors and precisely controls the gas flow rates throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. Trapping the VOCs helps create a smaller band of analytes traveling to the GC column, producing greater signal-to-noise ratios and lower area-to-height ratios, ultimately generating sharper peaks and having better sensitivity and resolution. Once VOCs are captured, the trap is heated and carrier gas is backflushed through the trap, causing the VOCs to desorb. The 6-port valve then directs the VOCs through the heated transfer line to the GC for separation and detection by the mass spec. The gas chromatography is one of the popular chromatography techniques to separate volatile compounds from a matrix. It is simple and it has high sensitivity in identifying and helping quantify volatile compounds. First the sample is introduced into a stream of inert gas or the carrier gas, which is usually helium. In our case, some are trying hydrogen. Sample compounds move through the column at a rate affected by the degree of interaction that each compound has with the stationary non-volatile phase of the column. And then compounds that interact more with the stationary phase are delayed and thus separated from the compounds that interact less. When the compounds are eluted from that column, then they can be quantified and collected through the detector like the mass spec. And what helps us determine the amount of each analyte in a sample? We use the internal standard technique. So we add internal standards and surrogates to the samples in a known amount. And then each internal standard is assigned to an analyte based on retention time and is used to measure the relative response. So who uses purge and trap? We're talking drinking water plants who are mainly using US EPA 524 series of methods, and wastewater treatment plants that are mainly using the US EPA 8260 or 624 methods, a lot of contract laboratories, and of course, other countries that have their own drinking water and wastewater methods, very similar to the US EPA methods, and they are easily adopted applications for our purge and trap. The trap is responsible for retaining the VOCs of interest during the purge cycle and then releasing them quickly to the GC upon heating. So there are a few basic things that all analytical traps need to do. Most importantly, it must retain all of the compounds of interest, but we don't want it to trap everything. We want our traps to exclude specific things like oxygen, carbon dioxide, and water vapor. We definitely don't want those to pass through the trap unimpeded because we don't want to introduce these to the GC, especially if we're using a mass spec. We want the trap to release these analytes quickly and easily upon heating. All of our traps will retain compounds of interest at room temperature, and then as they're heated, they'll release them. Think of our analytical traps as essentially packed GC columns. Like a capillary GC column, at room temperature, compounds move very slowly. And as you ramp up that oven temperature, they start to move through more quickly. Purge and trap, analytical traps, they essentially work the same way. Other things we would like our traps to do is to remain stable at those temperatures, from room temperature all the way up to those higher desorb temperatures. We heat our traps up to 250 or 260 degrees C during desorb. We don't want those adsorbents to degrade or break down, which could lead to them off-gassing volatile compounds that could potentially interfere with our analysis. We also don't want our traps to serve as catalysts for reactions, either with the adsorbent material or between other compounds of interest. And last but not least, we want our traps to be reasonably priced because they don't last forever and they eventually need to be replaced. They're consumables. All right, while most standard methods define the dimensions of the trap as well as the recommended packing materials, there are multiple packing choices that can be substituted as long as they meet the analytical requirements of the method. So there are a whole host of adsorbents that are available, and they range from materials such as 10X. There are some natural materials such as coconut charcoal and other types of charcoal. Silica gels common, and then there are other proprietary adsorbent materials, molecular sieves, carbo traps, really complex adsorbents that come from the GC column world. So how do we choose? There are a lot of options available. How do we know what's going to work best for our analysis? How do we choose a trap? Most of these adsorbents will have a relatively limited range of compounds that they will adsorb or in the efficiency at which they will work. So for example, 10X is a good general purpose adsorbent, but it's going to retain certain compounds better than others. And you can run into situations where one target compound can push another target compound off of the trap. So you won't get that complete list of compounds that you're looking for that get transferred to the GC for analysis. The way that we get around this is that we typically use for some of our general purpose applications, such as the US EPA 524 series for drinking water or 8260 for wastewater and soils and sludges, we use a 3-bed adsorbent trap like our number 9 trap that is shipped with all of our Purge traps. Those traps are going to be stacked in order from the weakest to the strongest adsorbents, so that while we are purging, those compounds that are easily retained, the ones more likely to push other compounds off the adsorbent bed, will be captured by the weak adsorbents. And those compounds that are more difficult to retain, such as the gases, for instance, will make their way down the bed to the strongest adsorbents, where they will be retained. And then when we go to desorb, we'll reverse that flow through the trap so that we never push those easily retained compounds into the really strong adsorbent. And we want to make sure that everything is released completely so that we get good recoveries and good sensitivity and for our analysis with minimal or reduced carryover. Right, and these are the characteristics for a great purge gas for VOCs. So it must be inert, meaning it can't react with the VOCs or anything else in the sample. It cannot be combustible or unstable, such as hydrogen. For our instruments during desorb, the trap is closed off and heated, and that builds pressure and can cause problems for such combustible compounds such as hydrogen or oxygen. So hydrogen can be used as a carrier gas because when we go into bake mode in our instrument, it doesn't build that pressure up. So it's okay. Purge gas must also be free of VOCs. Usually the standard is 5/9 pure gas. You don't want it to contribute to the total VOCs in the sample collected and then create false positives or contaminated blanks. Helium is the traditional purge gas of choice because of its superior inertness, stability, and capability with the and compatibility with the GCMS. But it can be somewhat expensive and occasionally difficult to get. So nitrogen can be a really good carryover or a really good alternative to helium because it has similar inertness. It has a low cost for cylinders and it has the ability for generators to produce it. Because nitrogen is a larger molecule, it goes through the GC column first, which can, occasionally have a minor effect on the purge efficiency and the mass spec vacuum during desorb and pump down, but it often provides a more than adequate purge efficiency for compounds of interest under our standard EPA parameters, especially the methods we'll be looking at. All right, and here are the parameters for the purge that help contribute to a very efficient purge. We will start with vapor pressure. But overall, first, I just want to mention that the more efficient of a purge that we can create, the better chromatography that you will see and the better results you will get. Typically, the chemical nature of the compounds of interest will affect the purge efficiency, like the vapor pressure. The vapor pressure is the pressure at which a liquid and its vapor are in equilibrium at a given temperature. The vapor is said to be pushing against the atmosphere. So in other words, the higher the vapor pressure, the faster the liquid evaporates. Components that have a higher vapor pressure will have a higher purge efficiency. So vinyl chloride and other gases have high vapor pressures. All right, solubility is next. Solubility is the maximum amount of substance that will dissolve in a given amount of solvent at a specified temperature. So if a compound is very soluble in a sample matrix, it'll be harder to remove from that matrix. A good example of this is methanol. It's very soluble in water, and it has a purge efficiency of about 10%. Next of our purge parameters we'll be looking at is temperature. There are certain chemical parameters that we can change or manipulate to improve the purge efficiency, and a good example of that is the temperature of the sample. So we can heat samples to drive them from the liquid or the solid phase into the gaseous phase. An increase in sample purge temperature always increases the purge efficiency with which VOCs move from the liquid to the gas phase. There is a trade-off though. The amount of water vapor that makes it onto the trap doubles for each 10 degrees C rise in sample purge temperature. So we will be adding a little bit more water vapor onto that trap if we rise the sample purge temperature. All right, and as we can see here with 112 tetrachloroethane in water, displayed are various purge temperatures and percent efficiencies. And you can see from the temperature jump from 25 to 40 degrees C, you can see a 24% increase in efficiency, but from 40 degrees C to 60 degrees C, we only see a 10% increase in efficiency. So what we see here is an opportunity for method optimization. We don't necessarily want to go for that highest temperature that our method allows or the highest purge temperature that our purge and trap allows because of that increased water vapor onto the trap, which is not good. And as we continue to increase the purge temperature, we aren't seeing as big of an increase in efficiency. Therefore, the amount of water that the extra water we are putting onto that trap isn't worth the additional recovery of our compound that we're getting. So it's definitely about finding that sweet spot for the compounds of interest. All right, and then next we have sample size. A reason why you might want to increase the sample size would be to increase your sensitivity to get more of that sample trapped and then sent to the GCMS. But remember, an increase in sample size requires an increase in purge volume. An example of this would be if the purge volume is not increased, then you can expect only a 70 to 80% increase in sensitivity for basically doubling your sample size for 100% increase in sample size. All right, Next, we have purge volume. You can also control the volume of gas that we use to purge. So the longer that we continue to sweep that headspace away, the more volatile compounds we can extract from the sample. When considering purge volume, first we want to look at the flow rate. Basically, how many minutes or amount of time that we are purging and how fast, which would be the flow. A fast flow means that more purge gas is used in the same amount of time, and a really aggressive flow can cause pressure issues or push compounds of interest deep into that sorbent bed of the trap. We also want to look at purge time. So the longer that we're purging, the more of that purge gas we're using. And if we purge for too long, it can waste a lot of gas. And then again, it pushes those compounds of interest deep into the sorbent bed of the trap as well. Therefore, as our purge volume and time are increasing, they get to a point where the response just starts to plateau. And eventually you start to lose response altogether because those compounds are getting stuck in that trap, in that sorbent bed of the trap, which could lead to a waste of time and gas, which is a waste of your resources. And lastly, we have the type of purge method. So a water method, typically using the sparger for the purge, and a soil method utilizing the in-vial purge available on the Atomics XYZ. If we have a liquid sample, the way we introduce the gas using a fritted sparger creates a lot of small bubbles, which introduces more surface area for that liquid to gas interaction to occur, and it leads to a more efficient purge. Sometimes that fritted sparger doesn't work to our advantage though, especially if we have samples that have a lot of sediments, like wastewater samples that could clog the frit. In that situation, we do not want to use a fritted sparger because that can cause a lot of carryover and contamination from sample to sample. In that case, we would want to use a fritless sparger, or we could use that in-vial purge, which I just mentioned is available on the Atomics XYZ. This does create larger bubbles, which is not as efficient of a purge, but it gets the job done and there is less concern for contamination and carryover, which it can take a lot of time to clean up those samples. For soil samples, the amount of time for mixing and the speed is really dependent on the soil matrix. For fine soils or clays, they require longer mixing or purge times with a less aggressive mixing, possibly an agitate. And larger particles like sand require shorter mixing or purge times with more aggressive mixing, like a faster speed. And humic soils require longer mixing or purge times. Methanol extraction is automated by the Atomics XYZ. It's the only system on the market to do this. It removes the need for manual labor and the chance for human error. And depending on the technique, it removes the possibility of losing volatiles during sample treatment, has the ability to add surrogate prior to extraction or as required by the method, and it complies with US EPA method 5035 for soils containing VOCs greater than 200 ppb in concentration. All right, so we've been able to go over a lot about how purge and trap works and how the different parameters you can change to create an efficient purge. But there are some shared features in our products of the Atomics XYZ and the Lumen Aquatech LVA that help decrease sample cycle time, therefore increasing your sample throughput. The improved trap box and trap oven design leads to easier trap changes, It also has a faster trap cool down time because of the air intake. So cool down time is reduced by 22% or more over the previous models. And we have focused a large amount of effort on improvements to our moisture control by creating the moisture control system fitting, which reduces water and moisture headed to the GC, reducing peak interference and increasing sensitivity and increasing the GC column lifespan, which extends routine maintenance intervals. This moisture control fitting can also reduce or eliminate the need for dry purge. The solenoid valve manifold, which has fewer plumbing connections, making troubleshooting easier. And lastly, the electronic mass flow controller, which allows for independent programmable flow control in all modes. Higher flow rates means less bake time, decreasing the sample cycle time for each sample. All right, thank you so much for joining me today. Please check out our website for all of our latest application notes. You can view past webinars and be sure to visit our online store. You can follow us on social media too. And please be sure to submit any questions that you have, and I'll be able to get back to you by email. Thanks. Have a great day.